Welcome back to Tech 259 from Monday, April 12th. In this video, we're going to talk about different classes or different designs of generators. But as we talk through these, it's worth remembering that every single generator design has to have three basic things. It has to have a conductor. That's where we're going to induce the voltage. It has to have a magnetic field, and it has to have relative motion between the conductor and the magnetic field. Those are the requirements for every single generator. It's got to have those things. But there's lots of different ways that you can accomplish that, different ways you can arrange the conductor and the magnetic field, and different ways you can create relative motion. And those different designs have different advantages and disadvantages that make them suitable for different types of generators. For example, the generator that you find in a wind turbine is going to be pretty different from the generator that you find in a natural gas plant or a nuclear plant or something like that, or even a solar thermal plant that's designed to produce electricity. They all have their different kind of advantages and disadvantages. And so it's nice to play around with the components of the generator to take advantage of the characteristics of the energy source, be it wind or solar power or nuclear or combustion of some sort, and so on. So let's go ahead and switch over to the slides, and we're going to talk through these different types of generators. All right, classes of generators, which just means different types or different designs of generators. So first of all, let's clarify this first. Our general assumption, remember, we have to have a conductor, magnetic field, and relative motion. Our general assumption, unless we state differently, is that the armature, that's the coils of wire where we're going to induce the voltage, we're going to put those on the stator, for example, this right here. And you've seen this diagram before. We've talked about it in a previous class. Remember that, yeah, it shows the red windings in two separate places, but really it's just one set of windings. It's wrapped around the top part right here, and then it goes back around and it goes to the bottom side. So same thing with the blue and the green windings. Really, we've just got three sets of windings, one for each phase, because this is a three-phase generator. And most generators are three-phase if they're any significant size, greater than, say, a household size generator. So our armature is generally going to be on the stator, and our magnetic field is generally going to be on the rotor right here. So why do we do that? What is the advantage there? Well, we talked about this in a previous class. If we use a design like this with a permanent magnet for the magnetic field, that's pretty nice, because that way there is no slip rings, there are no brushes to worry about, which means no maintenance of the brushes, no inspection, no replacement of the brushes. That's pretty nice. So this is an advantageous design right here, because there are no brushes and no slip rings to worry about and no maintenance to do on that. However, I did say this in a previous class, there is a problem with this. And the problem is how you're going to run an automatic voltage regulator, an AVR, like we talked about last time. There isn't a way, because you can't vary the magnetic field here. It's a permanent magnet. You can't change the magnetic field of a permanent magnet as you're operating the machine. So you can't really have a voltage regulator in this machine. So although this particular design has some big advantages, it also has a big disadvantage, which is you can't vary the magnetic field strength, which means that you can't vary the output voltage. So that's a big disadvantage. So we might actually use this basic design, but use an electromagnet with a coil of wire right here instead of the permanent magnets. And it's still better to use this design with the electromagnet on the rotor and the armature on the stator. That's still better than putting the armature on the rotor and the field on the stator, because the current that is going to have to go through the brushes and slip rings to power this electromagnet, the current to power that is going to be much less than the current that is going to go through the armature windings. So we'd much rather pass current through brushes and slip rings to power an electromagnet right here, to power the electromagnet for the magnetic field on the rotor. We'd much rather do that because our brushes can be smaller and our slip rings can be smaller and cheaper. Much rather do that than put the armature on the rotor, in which case the full current output of the machine would have to pass through slip rings and brushes. All right, so that's why I say, unless we say differently, generally speaking, we like to put the armature on the stator like this, and we like to put the magnetic field on the rotor. And that magnetic field could be a permanent magnet like this, or it could be an electromagnet with a coil of wire around a steel bar or something for the magnetic field on the rotor. Okay, so we're going to talk about 3 general classes, and we'll talk in more detail about each one of these. But in general, this is the way the presentation today is going to be organized. First, we'll talk about AC synchronous generators, which is what we've talked about so far. We've talked about synchronous generators up to this point in the class. We've also talked about DC generators. So we've talked in an overview of these 2 types of generators, but we'll talk in a little more detail about synchronous generators. I don't have a whole lot more to say about DC generators. There aren't that many different variations of the design, so I'm going to kind of skip over this for today. There's not much more than what I talked about a week ago, or whenever that was, when we talked about DC generators. And then we will spend some time today talking about something called asynchronous generators. And I won't go into detail right now, but we will spend some time talking about different kinds of asynchronous generators today. Within these categories, there will be a couple different types of AC synchronous generators. There really is just the one kind of DC generator, so I won't spend much time on that. And then there are several different kinds of AC asynchronous generators, also called induction generators. So we'll talk about several different kinds of these also. Okay, so our first topic, our first class of generators is a synchronous generator. And this is what we've talked about before. What we've talked about is how you have a magnetic field, and that is rotating if that's on the rotor. And then the rate of rotation is going to determine the output frequency. Remember, we had an equation, N equals 120F divided by P. So that applies to synchronous generators. It does not directly apply to asynchronous generators, but we'll get to that. We'll talk more about that in a few minutes. But with synchronous generators, we actually have the magnetic field is rotating around at something we call synchronous speed. Synchronous speed is the rate of rotation of the magnetic field. So we have a couple different variations of synchronous generators. We can have the magnetic field be created by permanent magnets. That's the exact same diagram that I showed on the previous slide. And like I said in the previous slide, it's convenient because you don't have brushes or slip rings, which is nice for maintenance and durability, but there's no way to control that magnetic field because there's no way to apply an automatic voltage regulator, like we talked about in the last class. So this is really uncommon for machines of any significant size, like larger than what you'd use to power a house. Because you can't control the output voltage very easily. So for utility scale machines, we don't usually use a synchronous generator with permanent magnets. All right. So we'll talk. You can use permanent magnets in an asynchronous machine, but we'll talk about that later on in this slide presentation. So then we said in the previous slide, I just got through saying this, we can replace that permanent magnet on the rotor with an electromagnet, like is shown right here. So here's armature winding A, phase A, here's phase B, here's phase C. And now we've taken out the permanent magnet right here on the rotor and put in an electromagnet on the rotor. So now we have to apply a voltage to get a current to go through this electromagnet. And of course, to get the current applied to the rotor to create the magnetic field, we have to have brushes and slip rings. So that's somewhat inconvenient. Now you've got brushes and slip rings to deal with. But like I said, this is still much better than putting the armature windings on the rotor, because the amount of current going through here to the electromagnet on the rotor is much less than what you would have from the armature if it was on the rotor. So if we have less current, we can use smaller brushes and smaller slip rings that are cheaper and easier to replace. And we talked about last time, we talked about how we control the voltage output, and we do that by controlling the strength of the magnetic field. And we do that by varying the amount of current that goes through this part right here to the electromagnet. So as I increase the amount of current going to the electromagnet and through the coils, the windings in the electromagnet, I'll get a stronger magnetic field, and therefore I'll get a higher output voltage. So I can control the output voltage by controlling the amount of current going through here. All right, and then the last one, number 3, is that it could be an electromagnet for the magnetic field, but it also could be something we call self-excited. So what this means is that we've actually got like a little mini generator that is used to provide the current that goes through the electromagnet on the rotor. So it's all self-contained on the rotor. All right, so on the rotor, we actually have a small set of windings, and that is rotating around, and there is a permanent magnet around that small set of windings on the stator. There's some permanent magnets on the stator. So we've got like a little mini armature that's rotating around on the rotor inside that set of permanent magnets, but all the output from those mini armature windings are doing, it's just being used to power or excite the main electromagnet, this right here. All right, so it's almost like we've got a little mini generator on the rotor where we are using the coils of wire on the rotor directly to power the windings that are on the rotor. So therefore, we don't have any slip rings or brushes, and we can control the amount of current that goes through the windings of the main electromagnet, this set of windings right here. So we have an automatic voltage regulator, an AVR, and it is rotating on the rotor. It's rotating on that same shaft. So because we can have the induced voltage right there on the rotor, that feeds into the AVR, which controls the amount of current that goes through the main set of windings that creates the magnetic field for the main set of armature windings, which are on the stator. Because I have that arrangement, I don't need to use any slip rings or any brushes. So that's a pretty convenient arrangement. And this is pretty common for large utility scale generators, like for nuclear plants and coal plants and things like that. It's a nice, convenient design. All right, the next class that we're going to talk about is DC generators, but actually I'm not really going to talk about it today because there isn't really much to add to the presentation that we talked about a week or week and a half ago or so ago. So just refer back to that presentation. You have the slides on DC generators. Remember the two main differences between DC generators and AC generators. We use a split ring commutator instead of slip rings. And we use more sets of windings on the armature. For this case, the armature usually is on the rotor. The armature of a DC generator usually is on the rotor. Remember, I said I would point that out specifically when that was the case, and that is true for DC generators. All right, why do we use the armature on the rotor for DC generators? It's so that we can use the split ring commutator and vary which which sections of the split ring commutator are connected to the brushes. So as the split ring commutator rotates around, different sections of the split ring commutator are connected to the brushes, which we use as the output from the machine. So remember, if we do that, and if we add a whole bunch of sections, a whole bunch of coils to the armature and a whole bunch of sections on the split ring commutator, pretty soon I get an output voltage that is fairly constant and fairly consistent that we can consider DC voltage. And if you need something that's really truly constant DC voltage, then you can send it through a filter, an electronic filter. And electronic filters are a little bit beyond the scope of this class, but we do talk about them in TEC 240. So if you're interested in AC circuit design and electronic filters and the operation of rectifiers and inverters, then I would strongly recommend TEC 240. It's a great class. I hear the instructor is really awesome in that class. So anyway, I'm not going to talk too much more about DC generators today because there's not that much to add from our discussion last time when we talked about DC generators. The next type of generator that we're going to talk about is called the asynchronous, also known as the induction generator. They kind of mean the same thing. So what does asynchronous mean? Well, it means that there isn't a direct correlation between the rotor speed and the output frequency. So what I'm saying is for the synchronous generators that we've talked about up to this point, the equation N equals 120F divided by P, that equation applies, and that tells you the relationship between the rotor speed and the output frequency, also based on the design of the generator, which means how many poles there are on the generator. But asynchronous machines operate a little bit differently. They don't work the exact same way, where if you increase the rotor speed by 2%, you'll get a 2% higher output frequency. They don't quite work like that. So this is actually really convenient for renewable energy applications. So this is why these are really important to this class in particular. And the reason for that is because we don't always have, well, we never have great control over the wind speed, right? You know, for example, of a wind turbine, we don't exactly know how fast the wind is going to be blowing 5 seconds from now or a minute from now. So it's really nice to be able to allow for a variability in the input speed and still produce the same output frequency. All right, so that's the nice thing about asynchronous or induction generators, is that there isn't that direct correlation between rotor speed and output frequency. Therefore, we can take a variable input speed, like say from the rotation of the rotor blades on a wind turbine or hydroelectric. This could apply to hydroelectric applications as well. We can take a variable speed input and we can use that to power the generator, maybe through a gearbox or something, possibly, wouldn't have to. But that goes into the generator. So I have a slightly variable speed input into the generator, and I can still produce a fixed 60 Hertz constant output frequency. All right, so that's why asynchronous or induction generators are really important to this class, because they're applicable especially to renewable energy applications of generators. So basically, in a nutshell, how does an asynchronous or an induction generator operate? Well, in general, the rotor might look something like this. This is actually the first type of asynchronous generator we'll talk about. And I think hilariously, this is sometimes called a squirrel cage, you know, like an exercise wheel for a gerbil or a mouse or a hamster or something like that. Well, these are a little bit bigger than an exercise wheel for a mouse or a gerbil. They're more like squirrel sized, or maybe a little bit bigger than that as well. But that's kind of what this looks like. It looks like an exercise wheel for a squirrel running around inside there. So I love that visual image in my head. And the big takeaway from today is that wind turbines are powered by squirrels. The generator inside the wind turbine is powered by a squirrel running on an exercise wheel. Hopefully that's not the big takeaway from today, but I do enjoy having that image in my head of a squirrel cage induction generator. Anyway, we've got this rotor. This is our rotor on the machine. And then around the outside, we have those coils of wire for the armature. So what we do in this type of machine, we connect the grid, the electric grid, to the windings, the armature windings. So we're actually applying the electricity from the electric grid onto the armature. All right, if you do that, if you apply an AC electric signal to the armature, you will get a magnetic field that rotates around the armature. If here's north and here's south, if I apply an AC voltage to those coils of wire, then as soon as I apply that voltage to the armature, I'm going to get a magnetic field that rotates around like this while I have that rotor inside. And what's going to happen is I'm actually going to induce a voltage inside this rotor. And then when I induce a voltage inside this rotor, I'm actually going to get current to flow inside this rotor. So I get current that flows through these rotor bars right here, and then around the end ring and through the other side. So I get current that flows, for example, like this. And then when I have current to flow, I get a magnetic field, right? Because we know that flowing current always causes a magnetic field. So now the magnetic field that is created on this rotor interacts with the magnetic field that is rotating around the stator. And now this rotor basically just gets dragged along. It basically just gets dragged along with the magnetic field as it rotates around the stator. So what we have just described, what I have just described to you in the last 1 minute is an induction motor. That's an induction motor. And we talk about that in TEC 240. Once again, we talk more about motors in TEC 240. So if you're interested, then feel free to take that class. But we can actually do something very slight to turn that into an induction generator. All you have to do is attach a turbine of some sort, maybe a wind turbine, maybe a hydroelectric turbine, anything to drive that rotor, this rotor right here, to drive it around faster than the magnetic field is rotating around on the stator. All right. So let me say that again in slightly different words, because sometimes it helps to hear it from with different explanations. So the armature windings on the stator are connected to the electric grid. All right. So we connect the armature windings to the electric grid. When we apply the electric grid to the armature windings, we're applying AC electricity to those windings from the electric grid. So that actually causes a rotating magnetic field on the stator. All right. We don't have any electrical connections to the rotor. The rotor is this inside there. But when we have that rotating magnetic field on the stator, that is relative motion. This is the conductor. So I've got a magnetic field, I got relative motion, and this is the conductor. So I create, or I induce a voltage inside this rotor. If I induce a voltage, then I create a current to go through this rotor. And if I have a current going through there, I create a magnetic field. Current causes magnetic fields. And if I have a magnetic field, this magnetic field on the rotor interacts with the magnetic field that's rotating around the stator. And basically, this rotor gets dragged along with the rotating magnetic field from the stator. All right, and that's an induction motor. If I then take a turbine of some sort and make that rotor rotate faster than what we call the synchronous speed, that is the speed that the magnetic field is rotating around on the stator. If I drive that rotor faster than the magnetic field is normally wanting to rotate on the stator, then I will reverse the flow of current and I will actually turn that into a generator. We call that an induction generator. So we can actually drive that rotor at a slightly variable speed. It can actually be rotating anywhere from the rotation rate of the magnetic field on the stator up to a little bit faster. It can actually rotate faster than the synchronous speed, that is the magnetic field rotating around the stator. And the faster I drive that rotor relative to the magnetic field that's rotating around on the stator, the more current I will push out of the generator back onto the electric grid. So basically, in a nutshell, what an induction generator is, it's really just reverse powering an induction motor. I mean, it's very much just the opposite of an induction motor. In an induction motor, we apply an AC voltage and we get rotation, rotation as the output. With an induction generator, we're applying rotation from a turbine of some sort, and we're rotating that rotor, and we're actually pushing electrical current back out of the wires connected to the generator. So an induction generator is reverse powering an induction motor. All right, so I think that pretty much covers everything on this slide. So what we have just described is something called a squirrel cage induction generator. Sometimes you'll see it abbreviated SCIG. So we're going to talk about 4 different kinds of asynchronous or induction generators. They're all kind of along those same lines that I just described. But the one that I was just describing in detail on the previous slide, that is a squirrel cage induction generator. And you can rotate that anywhere from 100% of synchronous speed, which means at the same speed as the magnetic field is rotating around the stator. Of course, if you do that, you're not producing any current. So if you're actually rotating the rotor at 100%, that means you're rotating the rotor at the synchronous speed, which means that it's not really operating as a motor or as a generator. It's not consuming electrical power, but it's not producing any either. So in order to make it operate as a generator, you have to spin that rotor faster than the magnetic field that's rotating around on the stator. And generally that is rotated somewhere between 100 up to about 105% of synchronous speed. If you go much faster than that, then you just induce a lot of stress and torque on the machine, and you're likely going to break the machine. You're going to destroy the machine. So it is variable speed, but it's only a little bit of variability. You can't deal with wide swings of variable input. So you need it's almost a constant speed. There's only a little bit of variability in the input speed for this particular type of generator. We'll talk more about each one of these in the next couple of slides. So the type B, or the second type that we'll talk about, is a slight modification of the type A generator. It just replaces that squirrel cage rotor with a rotor made from wires. It's a wound rotor. So we'll talk more about that in a couple minutes, but basically that just slightly improves the amount of variation in the input speed that you can deal with. The type C is a little bit more complicated. We'll talk about that when we get to it. But the idea, as we go down this list from type A, type B, type C, type D, you can see that basically we're getting generator designs that allow more and more and more variability in the input speed. That's a good thing because, we have variability in our wind speed input, and we have variability sometimes in hydroelectric speed input. And depending on your design, if you have a solar thermal plant or maybe a biomass plant, you might have variability in those as well. So any type of applications where you need to produce a consistent 60 hertz output with a variable input, these types of designs are applicable. And the farther down this list you go, the more variability they can deal with and still produce a constant 60 hertz output. All right, so we'll talk about the DFIG, doubly fed induction generator, in a few minutes. And then the last one is basically full variability. You can have almost any input and still create a nice smooth 60 hertz output. So this is the one that I just described, the squirrel cage induction generator. And here's what the rotor looks like. So this is all the bars that are going across. You can imagine a squirrel inside there that's running on its exercise wheel. And this is the schematic diagram. Here is our squirrel cage induction generator. This is the schematic diagram of a wind turbine that uses a squirrel cage induction generator. And this used to be really common. It was probably 20, 25 years ago now, but this was basically the way all wind turbines were, all the way they were built from about the 1960s through about the 1990s or so. This is really the way it was. What you've got here is called a soft starter. So basically what that means is that when you connect the grid, remember, we got to connect the grid to the armature to start, but that can cause some shock on the machine when you all of a sudden apply that 60 hertz AC. So what this does is it's a soft starter, kind of as its name applies. So it kind of gradually allows more current to be applied to the armature windings so that you can spin up the rotor gradually instead of just all of a sudden. All right, so it gradually applies voltage from the grid to the armature, and therefore it gradually allows more current to be fed back onto the electric grid as well. So it's like a, instead of starting the machine all at once, you're gradually starting the machine. That's basically what it does. We'll talk about this in just a second, why you have to have a capacitor bank, but you do for this type of machine. And then the transformer, we don't talk a whole lot about transformers in this class either, but basically they are designed to increase the voltage. In this case, they are increasing the voltage from whatever voltage you're generating at here, which is somewhere in the neighborhood of 500 to 600 volts usually. And then you are increasing the voltage, usually up to somewhere around 30,000 volts to put it on the collection wires that go into the substation. All right, so what else? What else can we say about this? All right, it allows a slightly variable speed, about 100 to 105% of synchronous speed, which again is the rotation speed of the magnetic field going around the stator. But if you get more than that, then you're going to apply too much torque to the machine and you're going to damage the machine. So it's only a slight variability. And like I said, this was pretty much the way all wind turbines were designed up until about 25 years ago or so. Some nice things about this, it's really simple. There's not a whole lot to this design, which also makes it really cheap. So this was a cheap design of generator that was used commonly in old wind turbines. So here are some pretty big disadvantages, and these disadvantages are why we don't use this design anymore. You will not see a brand new wind turbine that uses a squirrel cage induction generator because of these two main reasons. First of all, the almost constant speed, a little bit of variability, but not much. That causes a lot of stress on the drivetrain, which is the drive shaft and the gearbox and the high-speed shaft into the generator. So those causes a lot of stress on the drivetrain. As the wind is variable, it gusts and then it dies down, and then it gusts and then it dies down. And all those gusts cause a lot of stress on the drivetrain. If you could allow for a more variable speed input to the generator, then you could alleviate or reduce a lot of those stresses. And this last one, so we actually have to energize those armature coils from the grid. I've said that, right, a couple of times. So when you power those armature coils from the grid, those coils on the armature are actually inductors. And I know we haven't talked about inductors in this class. Once again, we do talk about that in TEC 240, but basically inductors require a certain amount of what's called reactive power, like we did talk about that voltage control. So we did talk about reactive power, and it turns out that to energize inductors requires reactive power to be applied from the electric grid. So as it turns out, this type of generator actually consumes reactive power. It produces real power, which is good, but it consumes reactive power. And that's not good, because that reactive power has to be produced by something, some other type of generator. So this is not good. Remember, reactive power is also what supports voltage. So this generator is not doing a lot to support the voltage of the electric grid. It's supporting the frequency because it has real power output, but it's not helping out very much to support the voltage of the electric grid. So what do you have to do? Well, what you have to do is counteract those inductors, because those armature coils are, a coil of wire is an inductor. So the opposite of an inductor, to counterbalance an inductor, what you have to do is apply capacitors. Capacitors do the exact opposite things that inductors do. So what you have to do for this design, you need to have capacitors either right there locally at the wind turbine, or sometimes you'll just have a big bank of capacitors at the substation instead of locally at the turbine. But somewhere in your wind farm or somewhere on the electric grid, you're going to have to balance out all the reactive power consumed by the wind turbine by incorporating a whole bunch of capacitors. All right, so capacitors actually produce reactive power. Inductors consume reactive power. So that's why we have this capacitor bank right here. All right, so these are pretty big disadvantages. These are not good. These, this number one bullet point here, this affects the durability and the lifetime of the wind turbine. This second bullet point here, this affects how nicely the wind turbines play on the electric grid. Do they play nicely with other generators or not so much? And the answer for this design is not so much. So that led to a slightly different design of generator. Same basic principle, all right? Not much has changed between type A squirrel cage induction generator and type B wound rotor induction generator, except what has changed is the rotor of the generator. So instead of our squirrel cage with our squirrel running on the exercise wheel inside the generator, now we have coils of wire. And the nice thing about these coils of wire, there's actually coils of wire through these rotors. And the nice thing about these coils of wire is that you can have a variable resistor. It's called a potentiometer, but basically what you can do is you can change the amount of resistance that these coils inside the rotor have. And if you can change the amount of resistance that those coils have, then you can change the amount of current that's going through those coils. If you want to have less current, then you can increase the resistance. If you want to have more current, then you can decrease the resistance from the coils of wire going through this rotor. All right, this was also pretty common. You know, this is like the next step after the squirrel cage induction generator, but it's still pretty simple. You know, so we're talking like the 1990s into the 2000s. This was a common type of generator for different types of brands of generators. We get a little bit more variability of input speed. It's not a lot more variability, but roughly speaking, you can now have your generator input at somewhere between 100% of synchronous speed up to about 110% of synchronous speed. So you get a little bit more variability than the squirrel cage induction generator. All right, some similar advantages that we had in the previous design. It's still really simple. You know, it's not quite as simple as the squirrel cage induction generator because now we have this variable resistance right here. So that introduces a little bit of complexity, but not very much. There's still no converter that we're going to talk about in the next type of design. So it's still pretty simple. And that means it's still pretty cheap. So maybe not quite as cheap as a squirrel cage, but compared to type C and type D that we'll talk about next, it's really cheap. The disadvantage here is that oftentimes your variable resistors are going to be not on the rotor itself. They can be outside the rotor on a stationary platform. And so if that is true, then you have to deal with slip rings and brushes. It won't be a lot, you know, they won't be massive brushes or massive slip rings because we're only talking about a small amount of current going through the rotor right here. But nevertheless, you got to maintain them. And then the next two are really the same as the squirrel cage induction generator. Yeah, you have a little bit better speed variability, but it's still pretty limited. So because of that, you still have stresses on the drivetrain. You know, as you get a gust of wind, you can't allow the generator to spin at a much higher speed. It's still limited to about 110% of synchronous speed. So that means you're going to have more mechanical stresses and torque on that generator and on the bed plates and, you know, down to the tower of the wind turbine. But it has a little more variability than the squirrel cage, so it's a little better than the squirrel cage design in this regard. But still, we haven't changed anything about the armature. So we still have this deal where we have to apply electricity from the grid to the armature windings. And to energize those armature windings, which are inductors, you actually have to consume reactive power, which means you have to balance that out somewhere, either at the turbine itself or at the substation with a bank of capacitors right here. The next type of asynchronous machine that we're going to talk about is called the doubly fed induction generator, or oftentimes just called DFIG. And this is a little bit more complicated, but it's also really common. Currently, this is probably the most common type of generator that you will see in a new wind turbine. I would estimate maybe 2/3 to 3/4 of all wind turbines nowadays are DFIG generators. And the big advantage of this, the biggest advantage, is that it allows a larger variability in input speed. So now if there's a lull in the wind, no problem, we can adjust for that. If there's a gust in the wind speed, no problem, it can adjust for that as well. So there's a lot more variability of the input speed that the generator can deal with and still be producing power at a constant output frequency. So let's talk through this step by step based on the schematic down here. So we've still got the electric grid through a transformer being connected to the armature windings on the stator. All right, that much has not changed. So we've still got windings on the stator around the outside. We're still applying the electric grid AC to the windings on the stator. So we have a magnetic field that's going around the stator at what we call synchronous speed. What has changed is the rotor. What's going on with the rotor? So now what we actually have is electrical connections to the rotor. So you can already see one disadvantage to this design. If we have electrical connections to the rotor, what does that mean? It means we got to have slip rings and brushes, but the benefits outweigh the disadvantages here. So I have electrical connections to the rotor on the inside, this inner ring, this is the rotor. And so you can see I have three-phase connections from the rotor on the inside to what we call our converter. And what the converter does is it converts AC, this is the AC grid side of the converter. It actually converts the AC from the grid to DC and then converts it to whatever frequency AC it needs to apply to the rotor. All right, so what it actually does, the converter here in this design applies a variable frequency, whatever frequency it needs at that time. It applies a variable frequency AC to the rotor. So I've actually got windings on the rotor, like I'm using an electromagnet. I'm using an electromagnet on the rotor, but I can control the frequency of the AC that is applied to the rotor. And if I control the frequency of the AC that is applied to the rotor, I can actually control the rate that the magnetic field rotates around on the rotor, all right? So what I've got is a magnetic field that's rotating around on the stator, right? And that speed is fixed. That's the synchronous speed. It's based on the 60 hertz AC that's coming from the electric grid. So my synchronous speed of the magnetic field around the stator is fixed. It's actually for designs in the US, I mentioned this before, but virtually all wind turbines that use DFIGs, which is really common in the US, have 6-pole generators, which means that if you use your generator RPM equation, you'll see that the synchronous speed is 1200 RPM. So the magnetic field is rotating around the stator here at 1200 RPM. But our wind speed, we don't know what our wind speed is doing. So we would like to be able to allow for a rotor speed that is variable. We don't want to have to operate that at 1200 RPM. We want to operate it at variable speed. So we can do that because we can control the rate that the magnetic field rotates around on the rotor. So if the rotor mechanically is rotating slower than 1200 RPM, the synchronous speed on the stator, then I can apply a certain AC signal from the converter to the rotor to make up for that speed and to actually make the magnetic field rotate faster. It's like the magnetic field from the rotor is equal to the mechanical speed of the rotor plus whatever rotation is being made up by the AC signal that's applied to those windings on the rotor. So the magnetic field on the rotor could be rotating faster than the rotor is mechanically rotating, all right? So that could make up for it, all right? Conversely, what could happen is if the rotation speed mechanically of the rotor is greater than synchronous speed, greater than 1200 RPM, I can actually apply an AC signal from the converter in the opposite direction. So I can actually make my magnetic field rotate the other way on the rotor. So if my rotor of my wind turbine is spinning at 1400 RPM mechanically, then I can actually apply an AC signal from the converter that actually makes the magnetic field of the rotor spin slower than 1400 RPM, more like 1200 RPM that I need to rotate with my magnetic field on my stator. All right, so basically the whole point is to use the converter to apply whatever frequency AC I need to apply at that time to the rotor to make it operate close to the synchronous speed and therefore push current out through the armature windings and to the electric grid. So initially to get this thing started, you're applying the electric grid to the armature windings, but then once this thing is operating, then you're actually pushing current out to the electric grid. In that respect, it's the same as the first two designs that we talked about. All right, so let's make sure I said everything here. It's called a partial converter because only part of the electricity is coming through here. All right, so the electricity that's being applied to or being pushed out of the armature never goes through the converter. That's why it's called a partial converter. The converter is only responsible for the electricity being applied to or produced by the rotor. That's why we call it a partial converter. So the rotation of the magnetic field on the rotor is controlled by the converter, and it does that by applying a variable frequency AC to the rotor. The converter can make the magnetic field on the rotor rotate slower or faster than the synchronous speed. It can do that by changing the frequency of the AC voltage that is applied to the rotor. So it can actually make the magnetic field rotate clockwise or counterclockwise, whatever it needs to do. It can apply whatever frequency AC it needs to apply to the rotor. And because of this, the rotation of the magnetic field on the rotor, can actually rotate faster or slower than the rotor is physically rotating, all right? So that's pretty cool. It's a pretty ingenious design, and it allows us to operate at a much wider range of speeds than the squirrel cage or the wound rotor design allowed us to operate. All right, the last thing, or one of the last things here is that it actually operates as a synchronous generator at sub-synchronous speeds. All right, so what that means is that below 1200 RPM, I'm using that example again because that's what most wind turbines in the US are. So below that synchronous speed of 1200 RPM, the converter is applying an AC voltage that causes the magnetic field to rotate faster than the rotor is rotating mechanically. And therefore, it's operating as a synchronous generator, and it's pushing electricity out to the electric grid. So we're applying, the partial converter is applying an AC voltage to the rotor, and that is creating an induced voltage in the armature windings and sending current back out to the electric grid, all right? It's actually the opposite in some respects when it's at super synchronous speeds. That means when the rotor is physically rotating greater than 1200 RPM, what actually happens then is you actually induce a voltage on the rotor itself, similar to what we did in the first two designs, the squirrel cage or the wound rotor. And in that case, actually, it's operating more as an induction generator because I'm inducing a voltage on the rotor windings, and we actually use that. That actually comes out of the rotor windings through the slip rings, the brushes, and then goes back into the converter the other way. And then the converter can actually take that, we don't know what frequency that's at some variable frequency coming off of the rotor, and it turns that into DC and then back into nice, clean 60 Hertz AC and applies that back to the electric grid. All right, so this is kind of, I know it's a little bit complicated. If you haven't seen anything like this before, and I wouldn't expect you to, then this is a lot to take in. But basically at sub-synchronous speeds, below 1200 RPM, the grid is energizing the armature, and then eventually the armature is going to have an induced voltage and push current back out to the grid. And we are using the grid to power the converter, and the converter applies a variable frequency AC to the rotor, which induces that voltage in the armature that pushes current back out to the electric grid, so it operates as a generator, not a motor. However, at super synchronous speeds, when the wind is blowing fast and mechanically my rotor is rotating more than 1200 RPM, I actually induce a voltage in the rotor, and I also induce a voltage in the armature, all right? So I actually have current coming out of the armature and the rotor. The current coming out of the armature just goes back onto the electric grid. The current from the rotor, we don't know what frequency it's at, so it goes back into the converter, and it gets converted from variable frequency right here into nice, clean 60 Hertz AC that we can put directly back on the electric grid. So at super synchronous speeds, we're actually producing power from both the rotor and the armature, which is pretty wild and pretty amazing, but it does work. And like I said this already, this is really common in modern wind turbines, which is why I'm spending the time to explain this. So definitely the majority of modern wind turbines use defig generators. All right, some advantages and disadvantages. The biggest advantage I already mentioned is that it can operate at a pretty wide range of input speeds. So now we can deal with wind speeds that are gusting or have lulls, and I can still maintain my same output frequency without getting large stresses on the drivetrain. So I have lower drivetrain stresses. That's a big advantage. And this is also a big one I didn't mention before, but because we have that converter and we can change the magnetic field on the rotor, this can actually produce reactive power. So this is another big difference, significant difference between this design and the previous two asynchronous designs that we talked about. This can actually produce reactive power, whereas the other ones consume reactive power. There are some disadvantages here. Like I said, it does have to use slip rings and brushes because we have to apply the variable frequency AC from the converter to the rotor, or if it's super synchronous operation, then we have to pull the induced voltage off of the rotor to get it back into the converter. So we do need slip rings and brushes, but they're not that big. They're nowhere near as big as the size of the brushes or slip rings you would need if the armature was on the rotor. Also, obviously, you have a converter. Converters are big, fancy electronic devices. They typically take up like several large cabinets, cabinets that are like 6 feet tall. It'll take up like a space that's, 6 feet by 6 feet by 3 feet deep, something like that. So they're complex devices. And of course, it takes energy to run the converter as well. So there's, some small efficiency penalty for that. But it's far outweighed by the advantages that you get from the defig generator. And as you would expect, because you've got a big fancy electronic device that we call a converter, it's going to be more expensive. So these machines are more expensive. So I mentioned before, how nice does the wind turbine play with other generators on the electric grid? This is much better. The defig machine does play nicely with other generators because it's able to produce not just real power, but it's able to produce reactive power and thus support the voltage on the electric grid. So this is a very good design. It's a little more complicated, as you can see, but it's a very good design with a lot of big advantages over those previous two asynchronous designs that we talked about. And as a result, it's a very common design. That brings us to our last type of asynchronous generator, and that is the variable speed generator with the full converter. You can just call it that. It's a really long name up here, but that's just showing that, well, kind of there's two different types here, but we're just lumping them together. We've got a variable speed machine with a full converter. So we're lumping all of the full converter machines together. It could have a wound rotor synchronous generator, or it could have a permanent magnet synchronous generator. So the only difference here is that you could be using a permanent magnet for the magnetic field, or you could be using a wound rotor electromagnet for the magnetic field. But either way, we kind of lump them together because they both are a variable speed full converter generator. So this is actually, it's simpler actually than the previous one, the defig. It's simpler than the defig. Let's look at the schematic down here. Basically, all that you have here is a generator, and the output of the generator comes from the stator of the generator, and the entire output from the generator goes into the converter. And so now all of the electricity, it's flowing this way from left to right. We don't have to energize these armature coils from the grid. It doesn't work that way. So we are actually producing electricity. We're inducing a voltage in the armature coils on the stator, and all of that electricity goes into the converter. It's a full converter because all of the electrical output of the generator goes into the converter. The only thing is that the electricity coming out of the generator and into the converter, we don't know what frequency it's at, because this design is intended to allow for a very wide range of input RPM from the input from the turbine, or whatever it is that's providing input into the generator. So we don't know what the frequency output of this generator is going to be. It could be almost anything, but then it goes into the converter and it's converted from AC at some unknown frequency to DC, and then back to a nice steady, even 60 hertz output. So the output from here, from the converter, is a nice 60 hertz output if we're talking about in the North Americas. We're talking about 60 hertz output. Still goes through a transformer because it's going to be at a lower voltage than we want to put on the transmission line. So we put it on the transmission line to go to the substation or the electric grid. So as you can see, this is actually a lot simpler than the DFIG design. Let's make sure I set everything up here. This actually has a lot of similarities to the synchronous machine. That was the first one. Those are the first ones that we talked about, where we said we could have a permanent magnet or an electromagnet. So the same thing is true here. We gotta have a magnetic field on the rotor, but that magnetic field on this rotor spinning around could be a permanent magnet or it could be an electromagnet, and both are common. Even in wind turbine designs, there are companies that use permanent magnets, type D generators, and there are wind turbine companies that use wound rotor or electromagnet type D generators. So both are fairly common. But either way, we've got a magnetic field that's rotating around here. And then we've got that rotating inside of an armature a set of armature windings. And that is the output of the generator that feeds into the converter. All right, so our magnetic field could be a permanent magnet or could be an electromagnet. We have pretty much fully variable speed, which means that the rotation speed of this turbine, the wind turbine, and the rotation speed going into the generator could be pretty much anything. It almost doesn't really matter, because it doesn't matter what the output frequency here is. We're going to take all of it and put it into the converter anyway. So if it doesn't matter what the output frequency is, then it doesn't really matter what the input RPM is. So that's really nice. It's fully variable speed. We said this, the converter takes that variable frequency AC from here, and then it rectifies it into DC internally in the converter, and then it inverts again into AC that we can put on the electric grid. Said this already, the input rotor RPM could be pretty much anything, which is really nice for, say, a wind turbine or hydroelectric, or maybe some other types of generators as well. Because this is really a synchronous machine, and that is to say that there is a direct correlation between the input RPM here and the output frequency here. All right, so it really abides by the generator RPM and the principles that we talked about in previous classes. You know, N equals 120F divided by P, based on the number of poles in this magnetic field right here, and based on the input RPM, you can tell me what the output frequency is. The thing is, it just doesn't matter. We just don't really care what this output frequency is, because we're gonna rectify all of it into DC and then invert all of it back into 60 hertz AC again. So even though it's really a synchronous machine, it's lumped into this category of asynchronous generators because it has this variable speed capability and it has this converter. So even though, you know, this part right here that I'm circling right here, this really operates as a synchronous generator, which just means there's a direct correlation between the input RPM and the output frequency, right? But it's different than the other synchronous machines, so we put it into this category of asynchronous machines. And because the rotor RPM, that is this right here, the rotor RPM doesn't really matter very much, this design sometimes might use a gearbox and sometimes it might not. It might not use a gearbox. If it does use a gearbox, then typically you'll have fewer poles on the magnetic field and thus a smaller, more compact generator. If it does not use a gearbox, then typically you'll use more magnetic field poles on the magnetic field on the rotor, and thus it'll be a larger generator, which usually means a little more expensive as well. But you really don't have to use a gearbox for this design. And basically, any modern wind turbine generator that is not using the DFIG is using this design. So I think I said for the defig design, maybe 2/3 to 3/4 of modern new wind turbines use the defig. The rest of the designs use this design, the type D variable speed with full converter. Some advantages and disadvantages of this design. Well, obviously an advantage is that the input RPM can be widely variable, even more widely variable than the defig design. So that means you have lower drivetrain stresses on your mechanical parts of your wind turbine, like the bearings and the attachment to the bed plate or frame of the generator and the gearbox, if you have one, and mechanical aspects of the generator have lower stresses. This is like the defig design. You can actually produce reactive power from the converter. The converter can produce reactive power. So it's a good design to support the voltage, and it's a good neighbor. It works nicely with other generators on the electric grid. The downside here, if it uses an electromagnet for the field, so it might not, but if it's using electromagnets on the rotor here for the magnetic field, in that case, then it would need to use slip rings and brushes. If it's using a permanent magnet, then it doesn't. You know, it's kind of, you know, half a dozen or 6 of one, half a dozen of the other. Why would you want to use a permanent magnet? Well, so that you don't have to use slip rings or brushes. Why would you not want to use permanent magnets? Well, because permanent magnets are expensive. So that's the trade-off there. And of course, another downside is, you know, we said with the defig design, the partial converter makes it more complex and expensive. Well, now we have a converter that's much bigger than we had in the defig design. So the converter is a pretty complex piece of equipment, and that makes it fairly expensive. So this would be the most expensive design of wind turbine, followed by kind of an order that we talked about. The cheapest is the squirrel cage induction generator, a little bit more expensive, but not much. Than that is the wound rotor induction generator. Considerably more expensive than that is the defig design, and considerably more expensive than that is this design, the type D variable speed with full converter. But as you can see, it does have some advantages. All right, that is the end of that presentation. A lot of the choice of which generator design to use just comes down to the strategy of the company that's making the wind turbine. But one observation that I have noticed is that for companies that are making turbines for offshore applications, it's really hard to get to those turbines to do maintenance or repair work on them. So one observation I've made is that for offshore wind turbines, oftentimes they want to get away from using a gearbox. And one way to get away from using a gearbox is to use a type D generator that we just talked about with a full converter. So it seems like the full converter type D design seems to be a little bit more common for offshore wind turbines, or maybe just turbines in really remote locations. Whereas the type C defig design tends to be more popular for most other applications where it's not that incredibly difficult to go and do some maintenance or repair work on them if necessary. But other than that, you know, choosing between the defig design and the full converter design, it's really just kind of down to company strategy, you know, what they think is going to provide the best marketability and how they can best sell their products. So that's about it for today's presentation. There is no homework for today because there really is nothing quantitative that I can ask you about this material that we talked about today. But your homework is basically to work on your generator project. Remember, that is coming due pretty soon. So be sure to come on into the lab on the testing day, as well as the work day, because I'd recommend trying it out before it's actually due. So if you want to try it out before then, you're welcome to. Just let me know when you'd like to come in, and I'll make sure the lab is unlocked for you. So let me know if you have any questions, and I'll see you soon in the lab.